Okay, Assalamu alaikum everyone. My name is Lara Samhan, and today we'll be talking about the red cell metabolism. So basically, let's get started. Is my voice clear?
Yes.
Okay, so basically, in regards to red cell, what is basically a red cell? Red cell is basically a biconcave shape, and this is the normal structure of the cell. I'll just open the laser. Okay. So basically, this is the normal shape of the red blood cell, which is a biconcave structure. Now, if there is any problem in this biconcave structure, basically we're going to have problems in the RBC to be moving from one place to another. For example, if we have any problem to the structure of the normal biconcave structure, we might have sickle cell shape RBC, which is basically like this thing. It looks like a moon or a half moon shape. Now, if we have this abnormal half moon shape, or if we have this sickle cell RBC shape, basically all of the RBC can get stuck in the capillary, which can cause which can actually form like a clot and cause ischemia or hypoperfusion to the organs. So the normal shape of the RBC is a biconcave, which is this one. If we have a spherical or a rounded shape RBC, it's abnormal. If we have an oval shape, it's an abnormal shape. And if we have a sickle shape, it's also considered to be an abnormal shape. So the normal shape of the RBC is basically a biconcave shape. Now, let's get to know more about the RBC metabolism and the role of the RBC, since our lecture is about the metabolism of the RBC. Now, basically, RBC is one of the things that doesn't have any nucleus. That means if it doesn't have nucleus, it's not going to have either neither transcription nor translation, so we won't be forming protein. So how will the cell, or how will the red blood cell actually have its energy? It's going to have its energy, or it's going to actually produce ATP through the process or through the pathway of the glycolysis, or in other words, the anaerobic glycolysis. Now, this anaerobic glycolysis is basically a pathway which at the end produces ATP. For each one glucose molecules, we end up with 2 ATP molecules. And this ATP molecule is important to maintain the structure and function of the RBC and have the RBC in a biconcave shape, and for it to be flexible and to be able all the way to move throughout the capillaries, throughout the veins, and throughout the arteries. Okay, so basically, if we have any oxidation that happens to the RBC, this thing is considered to be abnormal. Why? Because this oxidation thing is going to actually make the RBC to be non-functional, and it will cause it to be having more of the free radicals, which will actually might end up having the hemolysis of the RBC and the formation of a clot, which can actually lead to ischemia or hyperperfusion of the organs. Now, so basically, the anaerobic glycolysis, or the ATP, which is produced by the anaerobic glycolysis pathway, is important for maintaining the volume, the shape, and the flexibility of the RBC, which is actually responsible for perfusing the organs with oxygen, which is a vital thing. Tamam. As we said, oxidation is something bad. Once you hear the word oxidation, just remember free radicals, it's something bad. Once you hear reduction, it means that it's something very amazing, and it's trying to get the RBC to its normal structure. For example, if any oxidation happened to the RBC, we try immediately to reduce it or to do a reduction so that the RBC becomes functional and returns to its normal volume, shape, and becomes more flexible. So basically, we have over here the aquaporin 1. Once you hear the word aqua means water. So it's something in regards to a water, and basically this aquaporin 1 is a transport channel that transports the water, and it basically maintains the osmotic and the osmosis of the water entering all the way to the RBC. So we don't want lots of water to be entering to the RBC. Why? Because we're going to actually have a spherocyte or a circle-shaped RBC, and this is abnormal. We would like always the RBC to maintain a biconcave shape. Now, what happens, as we said, if lots of water enters to the RBC, we're going to have a spherocyte shape, or in other words, we can say we can have the hereditary spherocytosis. And this thing happens because we have a decreased expression of the aquaporin 1. Okay, so basically the RBC, as we said, has ATP by the process of anaerobic glycolysis. Each one glucose molecule in this pathway produces 2 ATP. Now, why this ATP is important? Because we need it in the NAK ATPase channel, and we need it in the calcium ATPase. Why this thing is important? So that we maintain the normal RBC shape, which is a biconcave shape. تمام. Now, if we have any problem in the NAK ATPase or in the calcium ATPase, that means we will have problem in the RBC, which could end with a hemolysis. Hemolysis, lysis means breakdown. So we have the breakdown of the RBC. تمام. So if we have a sickle cell disease, in other words, the RBC basically looks like a moon shape, which is an abnormal thing. This will cause the abnormal function of the RBC. Why? Because it won't be able to carry enough amount of oxygen and to transfer enough amount of oxygen. This won't be like functioning well. So we will have hypoperfusion to the organs, which will lead to ischemia. Tamam. Okay, so moving on. Okay, so in regards to the metabolism of the RBC, now as we said, we have this anaerobic glycolysis, or in other words, we can say the AMP. As we can see, this figure on the right-hand side is basically just part of the anaerobic glycolysis or the AMP pathway. Now, as we said, one glucose molecule produces how many ATPs? 2 ATP. And at the end of this pathway, as we can see, we have this lactate is being produced, and usually we have 2 lactate molecules that is produced in the anaerobic glycolysis. Now, if we have, for any reason, hemolytic anemia, hemolytic, as we said, is basically hemolysis of the RBC. So if we have this hemolytic anemia, that means the normal biconcave shape of the RBC will get abnormal shape. That means it will not perform its normal function to the body, which is actually perfusing the body with oxygen. So this thing actually won't let the RBC to be all the way squeezing itself through the capillaries, because the normal biconcave RBC shape is going to be flexible, and it has a flexible membrane. This flexible membrane allows it to squeeze itself wherever it was, either in a small capillary, in the veins, in the arteries. It can squeeze itself wherever it was. Like if it gets hemolyzed or if it has an abnormal shape, this will not let the membrane be flexible of the RBC, which will not actually let it to squeeze itself into small capillaries. So basically, we have 2 common enzymes that get deficient or that get that have a defect throughout the anaerobic glycolysis pathway, which is the pyruvate kinase and the phosphoglucose isomerase. The most common enzyme that actually gets defected in the AMP pathway or the anaerobic glycolysis pathway is the pyruvate kinase. طيب, يلا. Now, if this pyruvate kinase enzyme, which is the most common enzyme that gets defected, 95% of it gets defected in the glycolysis pathway, tell me in the chat, please, what's going to happen to the RBC shape? Is it going to be normal or it's going to be abnormal? Normal ولا abnormal? رائع, exactly. It's going to be basically abnormal. ممتاز. Okay, so moving on. Okay, so basically this figure is just something extra. It just shows in here the whole anaerobic glycolysis pathway, and over here it shows the HMP pathway. It's just for the sake of knowing how the pathways look like, and you guys already know that like it's something complex, so nothing to worry about in this slide. Right. Now moving on to the pathways or the metabolic pathways of the RBC, we basically have 3 main pathways, which is the we have over here the RLP, the EMP, and the HMP pathway, which is the hexose monophosphate pathway. So those are the 3 main pathways that the RBC uses. So let's move one by one. So basically we have over here, since we already talked about the anaerobic glycolysis or the AMP pathway, we said that this pathway starts with 1 glucose molecule, ends up with 2 ATP molecules, and the most common enzyme that gets defected in it is the pyruvate kinase enzyme. If this enzyme gets defected, that means we're going to have abnormal structure of the RBC, and the RBC isn't going to be able to perform its normal functions throughout the body. This is the number 1. Number 2, we have over here the RLP pathway. It's basically responsible for transporting the RBC that has the oxygen, and also if we have any case of ischemia or low amount of oxygen, in other words, hypoxia, or if we have any imbalances throughout the body, either acid-base imbalance or any other imbalances, this pathway actually tries to accommodate or tries to compensate and let the RBC as much as possible to be having the oxygen. And we have over here, how does actually this thing work? By accumulating the 2,3-DPG, or in other words, the 2,3-bisphosphoglycoronate. تمام. So anyways, to the hexose monophosphate pathway, this pathway is basically responsible for, it actually has the NADPH, and this NADPH is something very, very amazing. NADPH plus the G6PD, which is the glucose 6-phosphate, is really very, very, dehydrogenase is really very important. Why? Because those things are going to actually decrease the free radicals, or going to actually decrease the oxidation that happens. To be more specific, it's going to decrease the oxidation that happens to the RBC. So what if, for example, we have a free radical or oxidation that happens to the RBC? What's going to happen is that we are going to have the NADPH and the G6PD, they're going to try to compensate and remove this oxidation or the free radical that affected the RBC. Like, what if we have deficiency of this G6PD, or we have deficiency of the glucose 6-phosphate dihydrogenase? What's going to happen? We're going to actually have accumulation of the Haynes body. Haynes body is going to be like a spot that's going to be on the RBC. Tamam. And yes, so basically this is mainly it. So any questions so far? Any questions? All clear. Tamam. Okay. Regarding the person who joined late, don't worry, the session is recorded, so you can kindly hear the recording, okay? Or if you want, I can repeat everything at the very end, so don't worry. Okay, moving on. Okay, so we have a checkpoint over here. Are you guys ready? It's easy. Yellow. Right. So what's the most common enzyme defect in the anaerobic glycolysis pathway? So what do you guys think? A, B, C, or D? ممتاز, ممتاز, ممتاز. Bravo. You guys are excellent. طيب, if I told you the answer is A, are you going to tell me, am I correct or wrong? What do you guys think? Right, wrong? Is the wrong answer, exactly. Why? Because as we said, the most common enzyme defect is the pyruvate kinase. Pyruvate kinase is 95%, ولكن the phosphoglucose isomerase is only 4%, exactly. Okay, moving on. So basically, as we said over here, anything that's been oxidized is something very bad, tamam? So if we have a decrease or deficiency in the G6PD or the glucose 6-phosphodehydrogenase deficiency, what's going to happen? We will have Haynes body formation, and the free radicals are going to increase, and they're going to affect the RBC. Once the RBC has been affected, that means its structure, the normal RBC structure, will be changed, and it won't be able to do its normal functions, which is to transport oxygen effectively to the whole body organs. Now, G6PD is something amazing. NADPH is something amazing. Why? Because they reduce the free radicals, or they decrease the oxidation. Once we have deficiency in them, the oxidative stress or the free radicals is going to significantly increase, which is something very bad. Tamam? So basically, the G6PD deficiency is unfortunately more common in males than in females. Tamam? And this is more to their inheritance of their sex-linked. Tamam? Now, what else? So basically, we have what's the reason why we have deficiency in the G6PD, or for example, anything that might happen to the NADPH? The main reason is, for example, because of toxins that we may eat or encounter to it, or because of infections, or because of any disease or illness. Those are the main reasons why the G6PD can actually get affected. Now, what is exactly G6PD? G6PD is an enzyme, as you can see in here, that all the way it's an enzyme that moves the G6P, which is the glucose 6-phosphate, and it gets all the way converted to the 6PD, which is basically the 6-phosphogluconate. So this enzyme is really very important, and it actually removes the free radicals from the body, or removes the oxidation. And yeah, so it's very important. How does it do this thing? By getting or by reducing the NADP all the way to the NADPH. The meaning of reduction is basically adding H. From NADP, we added H, it becomes NADPH. Tamam. So yes, okay, so this is in regards to this slide. Moving on. So basically, what's the difference between hemoglobin and methemoglobin? As we all know, hemoglobin is like the main thing that we always hear in regards to RBC. We barely hear something known as the methemoglobin. Why? Because hemoglobin is like the main functional thing that's actually used in the hemoglobin, in the RBC itself. And it's really responsible for transferring oxygen from one part to the other part of the body. So basically, hemoglobin has the ferrous type of ion, which is Fe2+. لكن the methemoglobin is basically, we don't really like methemoglobin because it doesn't actually carry efficient amount of oxygen throughout the body, and it has the ferric type, which is Fe3+. So hemoglobin, we like it. Methemoglobin, we hate it. Okay. So we have over here the methemoglobin reductase pathway. We said if we hear the word G6PD, it's amazing. If we hear the word NADPH, it's amazing. If we hear the word reductase or reduction, it's amazing. Why? Because those things actually decrease the free radicals or decrease the oxidation in the body. Now, in regards to this methemoglobin reductase pathway, this is the diagram or the figure or the pathway of the methemoglobin. Now, we have this is the hemoglobin, which is a normal hemoglobin. It has hemoglobin Fe2+. This is the hemoglobin first hemoglobin normal. Now, if لا حول ولا قوة إلا بالله, an oxidant happen, or an oxidant just gets an oxidant gets encountered to an oxidant or a free radical, what's going to happen is going to turn to a very bad thing or a very bad RBC or a very bad hemoglobin, which is the methemoglobin, and it has the, as we said, the methemoglobin has the ferric type, which is Fe3+. Now, this thing is bad for the body. Why? Because it ineffectively transports the oxygen from one place of the body to the to other place of the body. So now the body, our clever body, tries to compensate this thing, and we don't really want this methemoglobin thing. So alhamdulillah, we get to know this methemoglobin reductase pathway, which is a good pathway that transfers all the way this methemoglobin, this bad methemoglobin, to the normal original hemoglobin that we actually want. Now, how this thing actually happens? It happens by two enzymes, which are almost the same. We have over here the cytochrome B5 reductase and the NADPH methemoglobin reductase. Those two enzymes actually get reduced. In other words, they have an H over here, which actually reduce this methemoglobin Fe3+ or the ferric type of the methemoglobin all the way to the normal hemoglobin with Fe2+. As we said, why? For example, we have an oxidant that happens. Oxidant can happen from anything, either infection, either drug, either toxin, anything. Any bad stimulus can actually cause this oxidation or the oxidant or the free radical to be happening all the way to the normal hemoglobin. Okay, so this is basically it in this slide. Moving on. So any questions so far? Any questions يا حبيب؟ No questions so far ما شاء الله. تمام ممتاز. Okay, so basically we have over here the changes in the RBC when it gets aging, or in other words, we can say the senescence RBC. Now, once this RBC gets aged, it's actually like the same as what happens with the individual. For example, whenever we age, we get wrinkles, we are less active. The same thing happens with the RBC. Now, once this RBC gets aging or the senescence RBC happens, everything bad is going to increase, everything good is going to decrease. So for example, in here, we have increase in the old cells. The bad things that are going to increase in the RBC is basically glycosylated hemoglobin. Glycosylated is from the word glucose. That means the hemoglobin has more glucose. Do you think this is like better, having more glucose in the RBC, which is like a diabetic? For example, diabetic patients, unfortunately, have very high glucose in their RBC if they didn't maintain, for example, their drugs, for example, taking insulin and the so what do you guys think, like having high hemoglobin is having high sugar in the blood is good? Yes or no? No, exactly. Exactly. So basically, having high sugar or glucose in the RBC is something bad. Mumtaz. And the RBC itself, the membrane of it, is going to be very fragile. And if it's going to be very fragile, that means it won't actually be squeezing itself through the, as we said, through the veins, arteries, or even through small capillaries. And it's going to actually, it can turn from a normal biconcave shape to a spherical shape, which is a circle shape RBC, and even a circle shape RBC is going to actually be bad. And even though we might think that it looks bigger, that means it transfers more oxygen, but it doesn't actually. It's actually the vice versa. It's not effective, and it doesn't actually carry more oxygen. It's actually very ineffective. Now, in regards to the good things that are going to decrease in the RBC is the enzymes that actually happens in different pathways of the RBC. For example, like the G6PD and other enzymes, as we can see over here, and actually the disc-like shape, biconcave disc-like shape of the RBC isn't going to actually be maintained. So all of those things are going to significantly be decreasing. So moving on, we have over here the erythrocyte. Now let's talk more about the erythrocyte. Basically, the normal lifespan of RBC is 120 days. Like this is, we already know this thing from basic science. After 120 days, it gets recycled. Every 120 days, it gets recycled. Now, once this RBC, for example, finishes its 120 days, what are the changes that's going to happen to the RBC? As we said, the membrane is going to get less flexible and it's going to be more fragile. The glycolysis or the anaerobic glycolysis, which is going to ending up by producing 2 ATP, is going to decrease. So it's going to have less energy, and the red blood cell is almost about to die. Tamam. So those are the things that are going to happen with the RBC at the end of 120 days. Like an average lifespan of RBC is 120 days. Now, how this RBC will get recycled? It basically either gets recycled intravascular or extravascular. Intravascular, that means inside the vessel. Extravascular is outside the vessel. But if it's outside the vessel, where exactly it's going to be recycled? It's going to be recycled either in the spleen or the liver or both of them. Liver and spleen are actually called as RES. RES is basically reticuloendothelial system. So we can call the RES or the reticuloendothelial system. They are basically the liver and the spleen. Those are the places where the RBC get recycled. Then why did we choose, for example, spleen and liver? Basically because both of them has macrophages, and as we know, macrophage is going to remove all senescence material for any senescence material, and one of which can be the RBC when it becomes aged RBC or senescence RBC. The macrophage is going to all the way engulf it and recycle it in the spleen, the liver, or in other words, in the RES. Now let's come to talk more about the intravascular and the extravascular. So we can have the RBC recycled in the intravascular. Basically, this is a normal RBC. يلا الحين after 120 days approximately it gets a senescence or an aged RBC, so it's time to tell it خلاص bye bye. Now it's gonna get lysed. This is inside the vessel. This is like a vessel. It's gonna get lysed inside the vessel, so the RBC will get lysed, and then after that it's gonna form a methymoglobin, and then after that it's gonna go to the kidney. The kidney is gonna all the way secrete it outside the body. This is in regards to the intravascular pathway. Now, in regards to the extravascular, which is in the RES, reticuloendothelial system, either it will get recycled in the spleen or liver or both of them through the help of the macrophage. Now, this is an RBC. RBC is like hemoglobin, tamam. So we have the RBC is going to get lysed, so we will have the globin, the iron, and the protoporphyrin. Each of them, for example, the iron will bind to the transferrin. The globin is going to be broken down to more as we know, globin is basically protein, so it will get broken down to its basic unit, which is the amino acid, and the protoporphyrin is going to all the way become an unconjugated bilirubin, which is going to go to the liver, and then after that, everything, the body is going to, for example, from the liver, it's going to go all the way to the gut, from the gut, it's going to go to the liver, from the, it's going to go to the kidney, from the kidney, it's going to be all the way excreted throughout the body in the form of urine. So basically, this is how the RBC gets recycled, either intravascular or extravascular. And then a new RBC is going to be formed from the bone marrow in the bones. Now, let's get to have a summary of the whole lecture. As we know, this lecture talks about the metabolism of RBC. So let's talk how the RBC basically gets formed. So as we know, RBC is going to be formed. This is the bone, this is kidney, liver, and the spleen. Now, RBC is going to be formed in the bone marrow. Once the RBC is formed in the bone marrow, through the help of the erythropoietin. Now it's going to be all the way sent outside to its places, to the vessels and to the vessels, arteries, and the capillaries. Now, once it's going to be outside, it's going to live approximately 120 days. It's going to do its function if it was in a normal size biconcave size now, or biconcave shape. Once this RBC خلاص 120 days already passed away, هلا it becomes a senescence or an aged RBC. It gets all the way lysed either intravascular or extravascular, تمام. And then after that, where it happens, extravascular either in the spleen or liver, and intravascular is going to happen inside the vessel itself. And then after that, it's going to be going all the way to the kidney to be all the way secreted to be all the way excreted as urine. تمام. So this is like a summary of the whole thing, how the RBC starts and ends. So let's solve the question together. Who would like to solve? You guys just read the question kindly and just throw your answers in the chat. Thank you. So what do you guys think is the answer? A, B, C, or D? Question says, تمام, C, A, okay. Any other answers? تمام, C, okay. تمام. طيب, the question says, which of the following is false? We want the false statement of the fate of glycolytic pathway. Now, we said we have in the RBC, we're going to have the anaerobic glycolysis. صح صح. يلا هلا we have A says glycolysis is the sole source of ATP in erythrocyte. We all agree that anaerobic glycolysis is the one that forms 2 ATP molecules in the RBC. So this is a correct statement. And the question wants the false one. So this isn't an answer. So A is correct. خلاص. B, deficiency of pyruvate kinase leads to hemolytic anemia. And we know that the most common enzyme that gets deficient is the pyruvate kinase. So is this thing correct? Yeah, it's correct. So if the pyruvate kinase, we have deficiency in it, it will cause abnormal shape and function of the RBC, which can cause hemolysis. So this statement is correct. Do we all agree till now? ممتاز. طيب, we have C says pyruvate generated during glycolysis is converted to lactate. As we know, I'm going to go back to the slide. The anaerobic glycolysis starts with pyruvate and ends to the lactate. So we have over here pyruvate and then lactate. So this statement is correct. So in the anaerobic glycolysis, we have over here pyruvate and we have lactate. So we end up with lactate and we end up with 2 lactate molecules. So this statement is correct. طيب, so D says pyruvate generated during glycolysis is converted to acetyl-CoA and enters TCA cycle in mitochondria. As we know, the RBC actually doesn't have the mitochondria, doesn't have nucleus. So how can this TCA cycle, or in other words, the Krebs cycle, happen in the RBC and it actually doesn't have organelles or doesn't have the nucleus? So this statement, do you think, is it correct or is it wrong? Exactly, this is the wrong statement. Because of that, the answer is D. تمام. Why? Because the red blood cell lacks the mitochondria for the conversion of pyruvate to the acetyl-CoA. Why? Because as we said, the RBC doesn't have mitochondria, doesn't have organelles, and doesn't have the nucleus. Okay, so moving on. So I would like to end, we're actually at the end of the lecture. Do you guys have any single question throughout the lecture? Okay, so basically we have a private messages. Okay, thank you so much. You're welcome. We have a private message. It says, what determines whether the RBC degrades intravascular or extravascular? Basically, the RBC can degrade wherever it want to degrade, either intravascular or extravascular. If it gets degraded extravascular, it will end up in the kidney. If it gets degraded in the intravascular, it will also end up in the kidney. So both ways are gonna lead to the same way. So like any way actually works, as long as it gets degraded. عشان إنه it's a senescence or it's an aged actually RBC, so it's already damaged. So yeah, so this is the answer of this question. Okay, so can you please repeat the key metabolic pathway? Yes, of course. تمام. Is it the slide? This one? Tamam. Okay, so basically, as we said over here, we have key metabolic pathways of the erythrocyte or of the RBC. There are three, mainly there are three. We have number one, the HMP, the hexose monophosphate pathway, the EMP, and the RLP. Now, the most important thing about the hexose monophosphate pathway is that it has the NADPH, as we can see in here, it has the NADPH. That's actually NADP gets reduced and it becomes NADPH by adding an H. So the NADPH and the G6PD, we really like it a lot. Why? Because it actually removes all free radical. It removes all oxidation that happens to the RBC. So if something happens bad and we have increased free radicals in the body because of toxin, because of drugs, because of infection, because of illness, because of anything bad happens to the body, it might affect the RBC. And once this RBC is being affected, that means we need a compensatory mechanism to remove this free radical from the RBC so that the RBC maintains its normal function and structure, which is actually to be transferring oxygen from one part of the body to the other. Because if this function isn't maintained, we're going to have hypoperfusion to the oxygen, ischemia to the oxygen, because there's not enough amount of oxygen, and can actually cause the death, necrosis, and gangrene to the organs. Now, we actually have this NADPH in the hexose monophosphate pathway. We have this NADPH that's going to actually be using the glucose 6-phosphate dehydrogenase enzyme. This enzyme is going to actually make the NADP to be all the way become reduced and have the NADPH. Now, this thing is very important to remove the free radicals. So what if something happened and we have deficiency in this G6PD enzyme? Once we have deficiency in this enzyme, that means nothing to remove the free radicals, nothing to remove this oxidation, this stress, oxidative stress that happens to the RBC. So we will have something abnormal in the RBC, which is known as the Haynes body. So once you see the Haynes body, just know immediately that there is G6PD deficiency. This is in regards to the first pathway of the erythrocyte. The second pathway is the EMP. EMP is the same as the anaerobic glycolysis. Now, once we have this anaerobic glycolysis, it starts with glucose, ends up with 2 ATP molecules and 2 lactate. So this is very important to be having the anaerobic glycolysis. Why? Because as we said, the RBC actually, it doesn't have this nucleus. So it doesn't have a place to produce, for example, glucose or to have power. So how is that RBC actually going to compensate and produce power or energy to itself? By having the anaerobic. Anaerobic, an means without. So without, aerobic means oxygen. So without oxygen. So we have anaerobic glycolysis. It's going to happen to be ending up with producing 2 ATP molecules from the glucose. Tamam? And the most common enzyme that actually can get defected in this EMP or in the anaerobic pathway is the pyruvate kinase. If we have defect in this enzyme, that means the RBC shape and function can actually get defected and it won't be functioning as its normal function and be transporting oxygen throughout the body. The third pathway is the RLP. The main function of this RLP is basically to be transporting oxygen from one place to another. And this transport of oxygen is going to actually be very helpful. Why? Because if we have any imbalance in the body or if we have any ischemia or hypoxia in the body, this RLP pathway is like a compensatory pathway that will avoid this thing from happening and try as much as possible to be delivering oxygen throughout the body. So these are like the three main pathways of the metabolism of the erythrocyte. So is it clear? ممتاز تمام. Any other question, doctors? Or future doctors, any other question? Tamam, you're welcome. So basically, I would like to end this lecture by giving a motivational quote, which is, your motivational whisper is stronger than the strongest wind to approach. We all actually suffer from different things, either academic, either non-academic, especially in first year. It's the very first, like some of you are UPP, some of you are direct, but each of us or each of you guys suffer from whatever thing. This thing is actually very normal. We all suffer from this thing. In each and every batch, we start with 500 plus minus, we end up 200 plus minus. Like this thing literally happens in each and every year. Like this is a scenario of Al University. So my only advice to you is, no matter what was your marks, either you passed, either you failed, either whatever happened with you, as long as you entered this thing, it isn't easy. And it's not impossible. As long, lots of graduates are already worldwide available. Lots of them are successful. Lots of them are already professors, scientists. Lots of them got Nobel prizes. So, like, what's the difference between you and them? It's actually nothing's different. We all have brains. But خلاص, they were insistent. They have this. They were consistent throughout their whole pathway or throughout their whole path to be something. And because they were insisting in this thing, they actually reached to what we see like right now. And because of that, they are one of our successful leaders and role models. So what I wanted to give you or to tell you is a very mini advice. No matter what was your mark, A, B, C, even if you got F, this is nothing. This is just a mark. Each of you know yourself internally how you are. Each of us, like, the best person to motivate yourself is yourself. No matter how much you have motivators all around, you are the only one who can actually push yourself the most. If your mark was the best, if your mark was the least, if you were the last, if you were the first, I don't care. What we care about is you trying to push yourself as much as you can. Because trust my words, not everyone who graduated just got the full mark. Lots of them actually failed once, twice, but they kept on continuing till endlessly. They suffered, yes, we all suffer. Nothing is easy. Nothing comes just with a flip of an eye. But we should always be consistent with what we want, to achieve. Just remember, it's just amount of years, 5 years, more than five, whatever. Like we really don't care about the amount of years as long as you are successful. I mean, like when you're gonna graduate, they won't really focus how many years you spend. They're gonna focus on what you are, how you're gonna help the community. Like really, the community needs you, needs me, needs us. So don't let anything or any negative thing or any bad memory that happened either from your marks, from your academics, just put you down. It's okay. We are down. We can be up. We can motivate ourselves. If you need help, call me anytime. Really, anytime before 12 a.m. After 12 a.m., I don't care. You want to call me, you want to send me a message, even if you don't have any academic question, you just want to call me, ask for advice. I personally, like, it's my ultimate pleasure really to help anytime you guys want. So my only advice to you is no matter what happened, because I really feel bad having this significant decrease in the amount of students. Just keep on trying. Just keep on pushing yourself. No matter what, it's okay. Keep on pushing yourself. Trust my words. When you reach, inshallah, very soon, you're going to be super proud and you're going to be a leader to others and to myself. And you're always my doctor, our doctor, and the community's doctor, inshallah. Future amazing, successful doctors, inshallah. So thank you so much. And if you guys have any question anytime, just please phone me, call me, send me WhatsApp, anything. I'm very open. So yes, good luck, inshallah. My future doctors, inshallah. So have a nice day. Thank you so much. Ma salama.